So thank you for introducing me. So I will speak about work with Brian Conrad on, so the title was given by Lucy. I should write, okay. So, spreading out of rigid analytic families and observations on p-adic Hodge theory. So this is a work which is still being written because there are some technical details which are not so clear. The motivation came from questions about rigid analytic spaces, in particular results on p-adic Hodge theory, which were proved by Scholz, extending the approach of faultings using perfectoid spaces. So in particular, if we have a smooth proper rigid analytic space over a non-Archimedean field, so a non-Archimedean field will be complete for a rank 1 valuation. So I will suppose that it is a discretely valued field with perfect residue field. So a usual local field that which is usually considered in the theory of Fontaine and others who looked at comparison using B. de Rham, B. Chris, and so on. So then there is there was a conjecture of Tate on which was originally formulated as Hodge-Tate decomposition. So in any case, one knows that by Scholz's work, so you have that the Z mod P is a finite dimension. The Z mod P cohomology is finite dimensional. In particular, the QP cohomology is finite dimensional. And then the comparison results give, well, in the sense of at least for dimensions, it gives that this is the sum of dim, like in the complex case, HPX omega Q, P plus Q equal N. And this is also dim of H and de Rham X using, so in particular, the Hodge to de Rham spectral sequence degenerates. And then one can ask the same question for a more general K. So a more general K could so here the characteristic, the residue characteristic is positive. The more general K could have 0 residue characteristic. It could also be something like the completion of the algebraic closure of QP. So in order to handle this, the natural idea is to use something which is like what is used in usual algebraic geometry to say that a variety over the complex numbers descends to a variety over a finitely generated Z algebra. So for example, there is, concerning the same question now in characteristic 0 for algebraic varieties, so there is a work of Delini-Lucy in, suppose 86, something like this. So they proved that the Hodge to de Rham, they proved without transcendental methods that is using reduction to characteristic P, the generation of the Hodge to de Rham spectral sequence, using spreading out to smooth schemes over Z. And so the idea is and this was also inspired by Falting's p-adic Hodge theory. So it is closely related to the material I'm discussing. So now the idea is that things that one can prove by the Delini-Lucy method for algebraic varieties, one should be able to prove using p-adic Hodge theory for rigid analytic spaces. So there was a further progress, so a paper by Lucy, Kato, and Nakayama in the log case. So for certain log smooth MAV, which are exact, so it's again a statement on the generation of the relative Hodge-to-the-RAM spectral sequence and local freeness. So this again should extend to the rigid analytic, as we hope, using some spreading out technique. So of course here we have more structure with log structure. So we must then spread out some schemes with extra structure to. So the idea is to. So for example, when K is an extension of QP, we want to. So any X over K which is proper is will be a fiber for a flat proper map Y to Z of rigid analytic spaces over QP. So here rigid analytic spaces could be in the sense of Tate, but usually they are quasi-compact and quasi-separate, and it's also in the sense of adic spaces or Berkovich spaces. So it's and then the fiber is over a K points, and also when you have some assumption like smoothness, then this morphism should be smooth. When you have a diagram, you should have a diagram. When you have some coherent shift, you have some coherent shift morphism between them, and so on. So for example, we would like to extend log structures, but this is not yet covered by the technique. On the other hand, this is more generally, you can have a discretely valued subfield of your non-Archimedean field, and you want to spread out. So you can also try to. Yes, you want to. Yes, so you can also generalize it slightly to what I spoke about with. Is it okay or?
Just lower it a little.
Like this? What? Okay, so when you have this is discretely valued, and suppose that x to y is proper flat map of rigid spaces over K, let us say quasi-compact and quasi-separate, and then by Renault flattening result, so this comes from a proper flat map of formal schemes, topologically of finite presentation over the ring of integer, which also flat over the ring of integer. And now you can restrict to some affinoid, so you can assume, let us assume that y is affine. So in the original situation, if this is affinoid, it doesn't mean that you have to blow up something. So then I want to say that this is a base change of a proper flat map of formal OF schemes with the same properties, topologically of finite type. And this will give, by passage to the general fiber, the result on rigid analytic spaces. So on the other hand, so I'm saying that to handle the problem and to handle also the RAM problem when the residue characteristic is 0, we need more. So suppose that I have a map from A to OK, where A is a Noetherian ring, adic, so complete for an ideal, and this is an adic map. So for example, we can take some finitely generated Z algebra and some mapping to OK, an element that maps to non-zero element in the maximal ideal. And then I want to spread out to, so then the same spreading out result. So when I have this formal situation, I want to get a proper flat map of topologically finite type formal schemes. So I recall that when I look at formal schemes, so I look at only formal schemes which are coming from ring complete for a finitely generated ideal, and then the locally something topologically of finite type is SPF of restricted formal series divided by an ideal, and there is a notion of formally of finite type where it's SPF of this with some formal series divided by an ideal. And in fact, the proof gives something formally of finite type, but then it is known by certain blowing up procedure to get things topologically of finite type. So now, so in the proof, I have to use deformation theory techniques, but there is a problem to make things sufficiently canonical. So I have to prove the existence of certain versal deformations, and this, in the situation of deformation theory that I want to look at, so is related to the notion introduced by Grothendieck of additive cofibered categories in his Springer lecture notes. So this was a work which, before Iluzzi's work on the cotangent complex, but his viewpoint, so I wanted to extract things related to his viewpoint from Iluzzi's results. So let me discuss general thing about Grothendieck additive cofibered categories. So suppose that I have okay, so C is an additive category. So I found a small modification of Grothendieck's formalism using a pro-object which gives a general statement. So usually it is an abelian category, and I want to consider certain cofibered category over C. So let us say E over C is a cofibered category. Again, all categories are small to avoid some set theoretic problems, and also I want to take pro-objects, so this will be a large category. Now, the condition of additive cofibered category is the following, that for the zero object I want to get a trivial category, and for let's say a product of two objects, I want that this is an equivalence. Now, once you put those conditions, you can introduce an operation on, so this is the fiber of E over X. So now when you have a morphism from X to Y, there is a push forward factor from EX to EY. So now we can, if you are given two objects in EX, you can, using this equivalence, get something in X cos X, and then use the sum up to go to EX. So this gives a kind of tensor product on EX. And then, so one can verify that EX is what is called later a strict Picard category. So the tensor product comes with associativity and commutativity constraints and the zero element satisfying all the rules, including the strict ones that you need about flipping in X cos X. So the strict Picard category is equivalent to a category of the following type. So I have a complex. So I will use Grothendieck notation, which is, I think Deligne used slightly different. So I have, let's say, a complex concentrated in degree 0 and 1, and then I let the objects be K1, and the morphism is given by something in K0. So if dx is y minus, so a morphism from Z to Y is an element in K0 of which satisfying this. So any strict Picard category is something of this type. So essentially you have to give something in the derived category of abelian groups of lengths 2. Now there are several conditions on those kind of, so there is the condition of left exact when C is abelian, and this means that when I have a short exact sequence in C, I can map EX, EY, EZ. So I have a point actually. So EX maps to the, so to speak, kernel that is the two fibered products of EY and the point over EZ, and I wanted this should be an equivalence. And if this holds, then more generally, when I have a square which is both Cartesian and co-Cartesian, then EX is mapped by an equivalence to the two fibered product. Now, so okay. So in fact, so for every additive co-fibered category E to C, so one can associate the left exact. So this is like a R0E. So this is like the construction of derived functors where you try to take the limit over all exact sequences. So you don't assume there are enough injectives, but roughly, if you have an embedding in something injective, then you take the EB, the kernel, so to speak, from EB to EC as a definition of R0E of A, and then you take a limit. Now, and then Grothendieck also extends the co-fibered category to complexes, but it is useful to extend it to pro objects. So E to C extends to maybe E prime over pro C by the obvious rule that you take E of a formal inverse limit as the 2 inverse limit of EXI, and this preserves left exactness. Now, there is the standard construction of such additive co-fibered categories in terms of length 2 chain complex. So suppose that I have an abelian category and a length 2 chain complex. Okay, then I want to define for x in C, I can consider home so the home from these two. Okay, and then I take the associated this was denoted in Grothendieck notes by Q, so something under double underline of L. So this is not necessarily left exact. So one can consider its associated left R0. Now, when we work with pro objects, we have we can use projective resolution. So the category of pro object satisfies the hypothesis, well, dual to AB5, as in Grothendieck's Toroku paper. So it is has enough projectives, and one can also construct them in some way directly. And so I can find the quasi-isomorphism in pro C, and then the R0 will become the Q of P1, P0, X. So the fact that P0 is projectives allows you to verify the left exactness, and also it turns out that the extension to pro C of switching the order. So let me. So if I am given A in the object of C and X in EA, so I can look at the problem of the functor of associating to B the morphisms from A to B with an isomorphism to 0 of the push forward of X. So by general consideration, when you have a left exact thing, this is pro-representable. So omega X is represents this. So if omega X is actually representable, then Grothendieck says that the typical complex exists. Now,
excuse me?
Yes?
What does the notation omega x stand for?
No, I don't know. I just looked at Grothendieck's book. I don't know why he. This is a very old reference, but I'm not sure if the generalities, in particular what I'm going to explain, I'm not sure if this is completely redone in more modern references, but I'm not sure what the omega stands for. I think it's just because of...
So it's just a symbol for the complex that you've written below?
No. So what happens is... No. The point is that given an element in ob C and an object in the cofibered category, one looks at the problem of making this 0 by mapping A to something. This is pro-represented universal by something called omega X. It could be represented. So in which case it is said that the typical complex exists, but it is easy to see that it is always represented by a pro-object. Okay? Now, so anyway, so you have a notion anyway of a maximal and quasi-maximal object in the additive cofibered category. So roughly, a maximal one is where for any b y over b, you want a morphism. So some object for which there is always at least one morphism to any other object. And quasi-maximal means that after embedding b in something, you have such a morphism. And then the result, for a left exact additive cofibered category E over C, so it is equivalent to R0 QL if and only if there is a quasi-maximal object and the typical complex exists. So this is part of other complicated thing. So now this can be simplified.
So what are the data here?
Okay, so this is, the data is, so I'm again, so suppose that I have an additive cofibered category and I gave an example, left exact. I have an example coming from an object, a two-term complex. And now I want to characterize those that come from a two-term complex. So anyway, this is one of the statements up to maybe some some maybe slightly different conventions in Grothendieck's book. So the condition is that for any a and x, there is omega x is represented and representable, and that there is a quasi-maximal object in the cofibered category. Okay. Now, now what I can show is that for every left exact additive cofibered category E to C, then E prime over pro C is equivalent to what is associated to a two-term complex with L0 projective in pro C. Okay, so actually this is almost tautological if I'm using, because you can, instead of using a maximal object, you just look at all possible objects in the total space of the category, kind of take fibered products and get a pro-object, which is in some sense maximal, except it is a pro-object. Then this will play the role of L1. Then the L0 will be the thing which pro-represent this omega, just relative to C, not pro-C. Then I will get a complex which gives the cofibered category on C itself. Now L0 is not necessarily projective, but I know that there is a projective envelope, so I can replace it by a complex where P0 is projective, and this is still maximal relative to C, so this again represents the same thing. Then I know it is represented by this on C, then I have to know it's represented by this on pro C. So this is a problem of inverse limits of those categories. So the problem, so it turns out that this has to do with the vanishing of lim 1 from P0 of some system. And this lim 1 is computed actually the proof gives it in terms of some standard complex, and this standard complex is exact in the category of pro-objects, and since P0 is projective, this is 0. So, okay, now, so in some sense, the maximal object is something which in the formation theory problems is like a versal deformation. So the property, so again I have to move is there a no.
It's okay.
So maybe this is a slightly different definition. So I will say that X in EA is versal if and only if it is maximal, and the following holds that if I have a surjection from B to C, and I have an object C in EB, and I have a map phi. So suppose that I have an isomorphism, then this can be lifted to some map. So I want the lifting of phi and of the isomorphism. You satisfy the obvious rule. So this is like the usual versality condition. So it is easy to see that if now, so the point is like this, that if, so I assume left exact, because otherwise, yeah, I want to, actually this is surjective, I want to pass to the fibered product, so it's natural to. So, so if A is maximal and omega A is projective, then, so AX, then it is versal. So the reason is that the map actually is defined up to, so the category is given by this complex, so the map is defined up to factorization by a projective, and since it's projective, one can lift, so that's not so. So in particular, for if C has enough projectives, then any good, so let us say good means is of the form R0Q of a complex. Any good additive cofibered category has a versal object. So now if one looks at the proof, one can also weaken it slightly. So we can say something is weakly good if the yeah, so if the group of so the EA modulo isomorphism is functorially isomorphic to X1 L A as above for some two-term complex. Yes, okay, for some two-term complex. Now, yeah, so now in so this will be, and then I still have a versal object, which is what I want. So it means that I have to prove a little bit less. So it depends on the formulation of the formation theory that I use. Sometimes I just use a formulation, I just control the set of isomorphism classes. So now, so the problem that I want to look at is the following. So I have x0 to t0. Let us say I have an Noetherian affine base, and this is affine. And this is some, let us say, proper flat morphism. And then I want to consider first order flat deformations over S. So let us say this is a finite type also. Flat deformations. And I want to construct a versal deformation for this in this. So this is defined similarly to what so now in every such situation, I have the ideal of T0 in T. So actually I will usually, well, it depends on the case, but usually, so one can either assume or not assume finiteness condition on I, but let us, to be in the previous context, let us just work. So we have in any case a fibered category over the category of T0 modules. No, I was too slow. Okay. So I have actually a left exact additive cofibered category over OT0 modules, possibly only finite type. And the problem is the same as constructing a versal object there. And so for this, I can use deformation theory like in Illuzy's book. So the idea is to, so here I have I, which is kernel OT. So the fiber over a module M are also those diagrams over S where the kernel from OT to OT0 is a given module. So this, so anyway, to the diagram X0 to T0, I get a topos, actually associated with this diagram, and then I have a morphism of toposes to S, as I say, Zariski. So this is actually then a deformation problem for this. So I will get, it's classified, so the solution is classified by something like, so I have the pullback of I to the total space. Now, so there is, so to control this, so there is a result which is based on Grothendieck duality, and which is the following. So I have now let us say a proper flat map where Y is Noetherian with a dualizing complex, then I have R home. I want to look at the polynomial like this. R home to, under some boundedness conditions. So suppose I have K is D minus coherent of X and L, actually D plus coherent, or D. So anyway, so it turns out that this is not like in the usual duality theorem, which is, well, there are several dualities. There is a trivial duality, and or the duality where you have F upper Schrick and some F lower sub. So there it's a twisted statement where this becomes R home of some operation on K L. Okay, so this is actually, so there are some generalization of this when you, instead of flat, you can twist by an F coherent, perfect bounded complex on X. So, so this statement is in some paper of Jack Hall, and I also found it connection with this. So actually I need it not for in this form, but for diagrams. So for this topos, mapping to S, but actually I have to construct because I want to look at all modules at once in order to identify so it depends on what one wants to do. So if one wants to calculate the isomorphism classes, then one needs some x1, one applies this, and one gets a home of something to the L. So now this is proved by writing L as a double dual of something and using various operations in the derived category, and one has to be careful about justifying things the right boundedness condition, but it is, and of course it should hold more generally without dualizing complex, but I'm not sure what are the right hypotheses. It's probably you need some approximation results, but then one would have to be in very fancy derived and higher context, so I'm not. But for our purposes, usually the rings have a dualizing complex. In any case, the existence of a versal deformation can be easily reduced to this case. So anyway, so this gives a weakly good condition on the additive cofibrate category. It's slightly weaker, but it's enough for versal deformation. This is one way. Now, if I use a more complicated, probably, if I use all finite type modules, kind of the category of all those, and make topos associated to larger diagrams, like in Iluz's work, so I have morphism of such toposes instead of, then if I do, probably, this is not yet worked out, then if one works out the analog of this for that, one will be able to have some upgraded version where one proves directly that the additive cofibrate category is given by this, which is now, so anyway, so this is some the first step in the construction. Then I have to work with, I have to construct nth order deformation, but this is relatively easy once you have the first order one. So again, I want to okay, so I'm in the same situation as above, x0 to t0 over s over, for simplicity, an Noetherian ring, things of finite presentation. This is proper and flat, but I don't assume dualizing complex because this is just for an intermediate step. Then I can consider nth order deformations, which are defined by the condition that the ideal to the power n plus 1 is 0. Then I want to define in a similar way a versal nth order deformation. And actually, I want a compatible system of such versal deformations which have the property that I have a kind of xn to tn such that xm to tm is obtained by modding by the kernel of O tn O t0 to the power m plus 1, where m is less than n. So the idea is that so if I construct xn to tn, then I can look at now, again, a versal first order deformation of this. Now there the ideal is of square 0, but I can make it small in the sense of the ideal, the kernel from the map to OT0 kills the ideal. So then I have a small kind of first order deformation of this. And then when I look at this and divide by the square of the ideal, I get something which is possibly fatter than the original versal first order deformation. So I have to contract something using the versality. And after one contracts, so one can check that this has the right properties. So now one can put all those things together, get a formal scheme. And then one uses the operation in rigid geometry to get what I said. Now, I want to explain some, in the few minutes, to sketch very briefly the applications to the problem about Hodge to the RAM and related things. So, so now what is the Hodge to the RAM in, let's say, in the complex case? Complex case. So X to S proper smooth of C-analytic spaces. Okay, but now we need some condition on the fiber. So I think that people know there is a class, I think, called Fujiki or something. Anyway, the bimeromorphic to Keller. So anyway, the result on Hodge decomposition extends to some, well, it's for Keller, but slightly, so it includes complete non-projective algebraic varieties. So in particular, I can have a proper smooth map of algebraic varieties. So in any case, so Delin proved in 1969 that, so using the absolute case, so he proved that those sheaves are locally free and the Hodge to the RAM degenerates. And the proof was by reducing to Artinian local situation and then using the comparison with classical cohomology. So here the natural idea is to use something like crystalline cohomology, but in the rigid context. But so the theory doesn't exist also in characteristic 0, but one can mimic it using just some check construction. So the strategy is like this. So if I have now proper smooth, let's say rigid case spaces, but it will also work in the Noetherian case. So I need to work in a context where I have basic operations on coherent sheaves and flatness notions. So either the classical rigid case or the Noetherian case. And then in the Noetherian case, I have enough what is called rig points, or points where I can actually pass the usual rigid-analytic spaces. So the idea is that I want to prove the local freeness and the generation. So, point by point, the idea is to use the spreading out technique to reduce to finite extensions of QP. And then the idea is to follow the Lin's argument, well, the philosophy, to go to Artinian local things. So now, so suppose S is Artinian local, and moreover, we can assume that its residue field is K. So K is characteristic 0. One can, but not residue characteristic 0, possibly. But it could be a residue characteristic 0. So now the idea is that I have a constant family over S, and the given family with the same special fiber. So morally, they should have the same crystalline cohomology. So I can construct a substitute of crystalline cohomology. So of course, this is in the rigid case, but locally, in any case, locally I have the affinoid in XS. I can embed them in some smooth affinoids over the base, and I can consider the completed de Rham complex. So V alpha completed along U alpha, and also for intersection, I take fibered product and complete along the intersections. Then I can consider a check construction from the completed de Rham complex. So let's say alternating check to make it finite. Then I get some candidate for the crystalline cohomology of the special fiber, so to speak. So one is to prove that, but this is like Poincaré lemma, local Poincaré lemma. So one is to prove independence of the covering, and that if you have a smooth lifting, it coincides with the cohomology of the smooth lifting, because you can take this as the only thing in the covering, and then they are isomorphic. So in particular, the de Rham cohomology is, the de Rham cohomologies are isomorphic, and so they have the same lengths, and for using this one can do the Lin argument. So, and this is the proof. So this problem is related again to p-adic Hodge theory. So in Scholz's work, he has a statement like this, but assuming the spaces are smooth and even with some twisted coefficients. So here the spaces are not smooth. So another question. So this is.
So the result is locally freeness and the degeneration.
Yes, this is one result, and so so another statement which one wants to is about the Hodge-Tate spectral sequence. So So now this is so X proper smooth over C algebraically closed non-Archimedean field over QP. Okay, and in this case, so what happens is that the Tal cohomology. So this is a bit technical. So the Tal first of all is finite dimensional for Z mod P and for QP, and so there is an étal in the sense of adic spaces, okay, so it's not the usual, but you have to define it in the, okay. Now, so this, of course, this is related, so maybe I am, is it minus Q or, yes. So in any case, what happens is that the p-adic vanishing cycle, so what happens is that it's related to vanishing cycles of, so when you tensor with, so one result is that it's related to cohomology of the sheaf O plus mod P, which also is, then the vanishing cycles of this, or mod P to the n, are, give you something which is related to differential up to some torsion. So one gets a spectral sequence, but one doesn't have enough Galois action to control the generation. So it could be that so one doesn't know that it degenerates up to torsion.
But with your previous result?
Yeah, no, okay, but now I think one knows in several ways, so I want to explain. So one way, if one knows it has the sum is of the same dimension as the RAM cohomology, so one has to relate this to the RAM cohomology, and this is not exactly in Scholz's paper, but one of the statements that he gave. So essentially, one spreads out X to a family over QP, over a smooth QP rigid-analytic space. Then one has the Gauss-Manin connection on the RAM cohomology, the filter thing. Then he constructs some B-RAM plus local systems, and you can pull it back. And I think that one can, probably his method gives a comparison result with this, so it has the same dimension as B. But I'm not saying that I didn't study this. And so on the other hand, another approach is to specialize at some point. So one wants to know that the dimension of this is the same as the dimension of the specialization. In other words, one wants to prove that the Rn F lower star Z mod P is locally constant. So for this, the idea is to prove some kind of Poincaré duality. So in the rigid case, so I want to look at this coefficient Z mod P. So I want to show that if X is, let's say, connected, then H2n X Z mod P is one-dimensional with basis given by the fundamental class of any point, and that the Poincaré duality maps are perfect pairing. Now, if you accept this, then you're looking at the class of the diagonal in X cross X, which can be defined. One will find that this is given by something like the Kunis formula, where alpha and beta are dual bases. And then one can spread it out to a neighborhood and compare things and find that those must be a basis in a neighborhood. So the main point, once you know the Poincaré duality, you get local constancy. And so to prove Poincaré duality, the idea is to tensor with O plus over P. So we have to prove Poincaré duality, or almost Poincaré duality, in fact. So the idea is that the vanishing cycles for this, for suitable formal modules, are kind of complexes with kind of almost coherent cohomology. And one wants to prove almost coherent duality for this. And the basis for, and the starting point is the case of a nice toric varieties where there are explicit calculations that can show the duality. And then, so one is to define the trace map. So the point is that this, so in any case, this is a long...
But this part is done in Falting using the assumption that the model is nice.
Yeah, no, okay. So, but now without knowing that the model is nice, the idea is like this. So you have the smooth, you can always assume that it is, the model is such that the special fiber is geometrically reduced, so generically smooth. Then you control the vanishing cycle shifts as being differentials up to torsion modulo, that is, modulo some small torsion, they're differentials on the smooth locus. You also know, so anyway, I have a model adapted to the perfectoid theory, so these things which are locally composition of finite état and rational domain. Anyway, then I have only vanishing cycle in degree 0 up to n, and the top one is a modulo of this small torsion is omega n on the smooth locus, but in particular it maps to the double dual of omega n, which is the dualizing complex. So I get some starting point, because this is the beginning of the dualizing complex. So I get And I also have Poincare duality on this. So I have a pairing from this tensor this to the top sheaf, going to the double dual, going to the relative dualizing complex. So I need a local theory of F upper Schrick for this kind of situation of restricted, like finite type and essential, or topologically finite type composition of such things. And so this is like the local theory, like in Archer and Conrad's book or the Stacks project. And I need the residual complexes for this. In any case, so to construct trace maps, then after one defines the pairing, one has to prove it's a duality. So the idea is to prove it in the nice situation, then to prove it nice situation modulo a free action of a finite group, and then to use Temkin's work to say that locally you have many neighborhoods which have a finite étale cover, so which is successive nodal vibration, and also equivalent for the group action. And then I have enough of those so I can, the idea is that both sides are kind of morally have some kind of cohomological descent, so so anyway, so this is again some kind of almost mathematics. It has to be made more precise, but so anyway, so this is one approach that I hope to speak about later.
Thank you.
Okay.
So we will take few questions. So first we will start from Tokyo, then Beijing, then Paris. Are there any questions in Tokyo? You see
Okay, are there
so far?
any
You
questions?
see them now.
Yeah. In the proof of the Hodge degeneration, the first theorem, so where does this co-5 dot category and cotangent complex enter? Is it in the...
No, so I have to construct a first order Versal deformation.
You look here now.
Okay. Okay. So I have to construct a first order Versal deformation and
Of what?
of x0 to t0. So I have x0 over t0. So the idea is that I have something over OK divided by some ideal, and I first use a standard reduction to finite type over Z, or finite type over the discrete valuation ring. But then I have to construct successive Versal deformation. So the problem is just the first order one. And the problem there is that the versality condition that I need is not just in terms of the functor of isomorphism classes, but with stronger things. So I can compute the group of isomorphism classes. So I need slightly finer information than is provided by, even if when I introduce the extra topos, I need slightly finer information. So one idea is that if one has this general thing on, well, it is easy to see it's left exact cofavored category. So if one has some general information on this, and this can be used well, in some cases, so it depends on the path which is used. In some cases, maybe one can use some cheap argument once one knows representability by pro-objects. And so, for example, I have this weakly good additive cofavored category which has a Versal object. So this can be used to prove the existence of a Versal. But it is the point that originally this was just motivation, but it turns out that knowing each fibers, so the point, if you know each fiber is equivalent to the category defined by a two-term complex, and you know, and then for a morphism you have, so anyway, suppose you just prove the thing in terms of canonical isomorphism in the derived category. This doesn't carry enough higher information to deal with situation with three objects in the base category. So it will not give a sufficiently rigorous proof of the Versal. So So then one has to find some way around it by passing. So but in any case, if one works with the topos coming from diagrams, one can probably get around it, but one has to be careful. If one is less careful about, so maybe using this weakly good notion one can do. So it depends. I mean, it has to be fixed in some way, but there are several small technical alternatives how to do it.
Thank you. So, are there other questions from Tokyo?
Are there some other questions? No, that's it. No,
Okay. So, are there any questions in BG?
Okay, so I have a question.
Yes.
I'm a little confused on the last part, on the Hodge-Tate spectral sequence.
Yes.
So, do you want to say you can prove this degeneracy of Hodge-Tate spectral sequence by using spreading out, or do you prove something new?
I don't know. I thought about but it turns out that I don't. So some time ago I thought about this. So just without knowing that it will follow if one proves that the dimension is locally constant. Then I tried to prove the dimension is locally constant by using almost Poincare duality. But I think that actually one can prove the degeneration without this by looking at what this p-adic Hodge.
Following the same proof, you mean, of let's say Fatings or Schwartz directly in this case.
I think this is, in any case, some of statement announced by Schultz was that over.
Statement is known if you work over something like QP or finite extension of QP, but we don't know it over C, and the result is to go from QP to C. So this is the new thing.
I see.
So this is the new thing.
Okay.
So in any case, without looking at, I think that, one way is to accept to just use as a black box the equality of the dimension for finite extension of QP, and then try to prove that this gives a locally constant shift, but using that's the beginning of the Schultz's approach relating to O plus over P without using all the period shifts. And then there I want to relate it. I want to use ideas on almost coherent duality to handle that. So this is one way to.
A long project. Okay. So, are there other questions in BG?
I think no.
Okay.
No other questions.
Are there questions in Paris? So, since we are maybe a little bit short time, let's thank the speaker again.